All right, welcome. This is going to be an exercise video where I want to explore context-free grammars for a couple of common languages. So let's start with a very simple language, or at least simple to define, which is Sigma star. And I maybe should mention before I get started that at least for this video, we're going to be looking at Sigma is the binary alphabet, our default alphabet. Okay. So I want to begin again. We're going to design a grammar, okay? And to design a grammar, I'm going to use the start variable s since that's our convention. But I want to make a grammar that's going to make any possible string I want. And there's a couple ways that we can do this, but I've kind of got a default one that I'll share first, which is first I want my string to be able to get longer if it needs to. So I'm going to use this duplication rule. S can become two copies of itself. Now that if it can follow that rule as many times as it wants, you're going to get a big long string of however many s's you need. And then once I've got a string of s's as long as I want, I can put the terminals in. I can start replacing them with zeros or ones, whichever ones I need for that particular string. Now this particular rule set here is pretty good. It produces almost every single string in this set Sigma star, but it is missing one string. Let you think for a second what it is. To make Sigma star, we need to remember that epsilon is also in that language Sigma star, and if we want s to be able to produce epsilon, we usually need to make that rule explicit. Okay, and so that's what we've done here. So I think that's a good example of our first language Sigma star. Now, one of the reasons why I wanted to make this as a first example, not just because it's kind of easy and it gets us a little practice, is it's common that sometimes in our other grammars, at some point we're going to say, oh, and then this part of the string I want to be anything. And if I want this string to be, this part of the string to be anything from the language, I need this grammar as a subgrammar somewhere in those other grammars. So I just wanted to highlight that. So as we keep going, maybe we're going to need this as a subgrammar somewhere else. I'll also mention this isn't the only way to make this grammar. Let's try a different one. Here's another one that I've seen before. You can go S0, S1. That's sort of combining these together, right? And that's saying, okay, keep replacing, keep replacing, keep replacing. Okay, and then eventually, I think you could just do it with an epsilon now. And that would allow you to make any string you want, okay? The fact that I put the zeros after, it could be 0s, 1s, epsilon, okay? And then there are ones with even more redundant rules. Okay, we could have SS, 0s, 1s, 0, 1, epsilon. That still does it. It's just got a lot of extra rules. I kind of maybe like these ones better because they only got 3 rules now. Okay, this one too. But this one here, too long. This is the one I tend to use in my own work when I'm doing it just because I feel like it's super straightforward and it's easy to understand how it works. Let's try another language here. Okay, here's another one. W, all strings W such that W has at least 3 ones. Now this is an interesting language too, because one thing we know about this is it's regular. When I have something that's regular, I think maybe I can make a regular expression for it. So I'm thinking, okay, how would I make this regular expression? I want to put a 1 in, I want to put a 1 in, I want to put a 1 in. Once I have my 3 ones in there, I can put in anything else I want. Sigma star, Sigma star, Sigma star, Sigma star. See already how the Sigma star is showing up as part of our definition here. This is still a regular expression, but let's see if I can make a context-free grammar that has that same format. Now what I'm going to do here is I'm going to make my start variable s, and I kind of want it to follow this pattern. So I want my 3 ones in there somewhere, 3 ones. And then I want some other rule that's going to do my Sigma star. So I'm going to call it U for now. U goes into all those places. And now I need U to do Sigma star. Oh wait, how do I do Sigma star? That's why I did it up above. Okay, so we go U, 0, 1, epsilon. We're good. We've got we've used the sigma star idea from above, plus some idea about regular expressions that we know to inform us how to build our grammar properly. Okay, so again, if it's a regular language, building grammars for it might be a little bit easier since we can build, for instance, regular expressions. Okay, let's try another regular language. The length of W is odd. If we were making this as a regular expression, what would we do? We would do sigma, sigma, star. That's an even number. Put another sigma on there. Boom. Okay, let's see if we can try this. So for this one, I think I'm going to work a little bit backwards. One thing I do need is something to do the sigma. So I'm going to make the sigma, I'm going to make this variable called u, that I'm going to say u can be a 0 or a 1. Okay. And then I'm going to say for my start variable, one of the things you could do is, well, you could just be a u by itself without this other stuff. That would just be this element. Or you can have this other stuff that goes on before you and plus one extra copy at the end. And I'm going to call that a d from another variable, and u, where u is making this extra copy. Here there's no d. Here there is a d. Now what's d supposed to do? D is supposed to be some even number of u's. So if I could make it, for instance, uu, and I follow this rule, I would end up with 3. Okay, but now what I want to be able to do is make the d's have as many of these pairs as possible. So now I can make as many d's as I want, but all those d's have to be replaced with 2 u's. So eventually I'm going to end up with an even number produced by d plus the one extra produced by u. This covers the case where I just have 1. I don't know if this is the simplest grammar for this particular one, but it's the one that I came up with looking over at this regular expression here. Okay, let's look at another one here. W starts and ends with a 0, 0. Okay, so we probably looked at this, another regular language. We probably looked at this one before. The string 0, 0 by itself starts and ends with 0, 0. Okay, that's interesting. The string 0, 0, 0 starts and ends with 0, 0. These are special cases that I'm trying to highlight up front. Okay, but after that, what you have is something that looks like this. 2 zeros at the beginning, 2 zeros at the end, and a bunch of random stuff on the inside, including possibly nothing. These ones don't have that form. Okay, neither of these two up above have that form. So if we were making a regular expression for it, I would make this one. Okay, so that means if I'm going to make a rule, these unions in the regular expression are ors. We already have ors built into our rule. We could say s is equal to 0, 0, or 0, 0, 0, or 0, 0, let's call it p, I don't know, 0, 0, where the p is supposed to do all that extra stuff. Okay, let's do p. P is supposed to do sigma star. We did that above. PP, 0, 1. Do we need epsilon in this case? Looks like we do in case we want that one to disappear out. Okay, starts and ends with 0, 0. We got the special cases of starts and ends with 0, 0, plus the general case of starts and ends with 0, 0. Okay, again, some tricks there that we can exploit from looking at a regular expression, but again, we were looking at a regular language. All right, let's look at the languages we've looked at so far have all been regular languages. This language here is the first one that's not a regular language, but it is context-free, as we'll show when we give a context-free grammar for it. Let's remember what a palindrome is. A palindrome is some string W that is equal to its own reverse. This is an interesting way of writing reverse, and when we're talking about strings, we don't talk about strings super much until we are in computer science, but sometimes we do care about the reversal of the strings. We just use this superscript r, like an exponent, that means the reverse of the string. And what that means is you got a string like this one, 0, 1, 1, 0, that if you read it forwards, and you read it backwards, you got the same string. That's what a palindrome is, okay? So we want to make a grammar that produces palindromes, okay? Now this is a palindrome, but I should mention this is an even length palindrome. There are also odd length palindromes. Put 1, 1 in the middle there, or we could put 1, 0 in the middle there. It doesn't matter. These are still read the same way forwards as they are backwards, okay? And maybe we would notice that in a special case, that means this string is a palindrome. This string is also a palindrome. So is this string, the epsilon, the empty string. Read it backwards and forwards, it's still empty. So those are special cases we want to make sure that at the end we might want to double check, okay? So let's make a grammar. Let's get a start symbol going here. And let's think about how our palindrome is going to work. Luckily, remember when we did 0, S, 1, we put zeros that grew to the left and ones that grew to the right. We could do the same thing here, except this one we put mismatches on the left and the right. We could do matches. So every time we put a 0 on the left, we also have to put one on the right. Every time we put a 1 on the left, we also have to put one on the right. Okay. So this pattern will make sure that the symbols on the left and the symbols on the right are always matching up as long as we go from outside to in. That's how the string will be built, from outside to the middle. But now when we get to the middle, we need to think, what can we put in the middle? Well, in even cases, we put epsilon in the middle, but in odd cases, we put a 1 or a 0 in the middle. It doesn't matter. Turns out it doesn't matter. We can put any of those things in the middle. When we get to the middle, we decide, do we want to put a 0 in there? Do I want to put a 1 in there? Or nothing at all to get an even length string? You'll notice, I mentioned these are our special cases we should check out. Can we make an epsilon from S? S goes straight to epsilon, good. S goes straight to 0. S goes straight to 1. We can make all of our special cases. So the grammar, we don't need to do anything special to it. It's already got it built in when we made our general case. So this is, again, this is a context-free language, but not regular. If you wanted to, you could use the pumping lemma to show that this is not a regular language. Okay, let's look at another one now. So this is, again, a context-free language. It actually has a bunch of blocks. It's got 1, 2, 3, 4 blocks. And usually when you have 4 blocks like this and you got variables up there, instinct, good guess is this is not context-free language. We'll see that in a future video as well. But this one ends up being context-free. So, and it's because of the relationship that we set up here. That is that the outermost block must be matched up with the outermost block on the right. So the one on the left with the right and the one on the middle are matched up to each other. That means we can still grow our string out from the inside, right? We'll grow the outermost block first, then the innermost block. We're probably going to need a couple rules for this. Let's do the S, the outermost block first. It's going to add these zeros and ones on to get started. So we'll do that with a pattern like this, zeros and ones. Replace them, okay? But eventually, you're going to want to get to the inner block. Okay, I'm going to call that one U, okay? We'll replace it. Once we're done putting all the out, we follow this as many times as we want. Once we're done, we'll go to U. Now U's in charge of doing the inner block. And it's got ones on the left and zeros on the right. Okay. And eventually we want to terminate it with epsilon. Again, I like to go and check, hey, is epsilon in this language? Well, if I pick 0 for N and for M, then I should be able to get epsilon. Can I get it from my grammar? S goes to U, U goes to epsilon. Good, I like it. Okay, so I think this works out. Again, test it for some derivations if you don't believe me, especially if you think we maybe got these two out of order. Sometimes it's hard to think of what, we're building things from the outside in here. So feel free to test that if you need to. All right, here's another one. This is an interesting one, okay? In this language, we're going to say all strings W where the middle symbol of W is a 0. Now, think again, this is not a regular language. So if you think, how could I make a DFA or a regular expression for this? You can't. It's impossible. There's no way to do that. But we can't make a context-free grammar. And again, it's because if we build our string outside in, then at the very end, we'll be in the middle, and that's the one that we're looking for. So again, we want to be able to build any string we want where the middle symbol is a 0. So we're going to build it from the outside in. Remember, with our palindrome, we would do something like this. Put 0 on the front, 0 on the back. 1 on the front, 1 on the back. Those will make sure they're always matching, but in this case, they don't have to match. We could have 0 on the front, 1 on the back, or 1 on the front and 0 on the back. That's fine. All that matters is that we're always producing 1 on the left and 1 on the right. Doesn't matter what symbols they are. If we're always putting 1 on the left and 1 on the right, then we know we're always in the middle. We'll always be in the middle of the string. So at the very end, once we've generated all the strings we want, we put a 0 in the middle. Interesting case. Let's try a special case of this. What's the shortest string in this language? Well, that's the string 0. It has a 0 as the middle symbol. It's the only symbol. And sure enough, we can generate it. Here's another one. The string 0, 0. There is no middle symbol in this one. This should not be in our language. Can we generate that? Well, we'll get 0, 0. No, the only way we could get 0, 0, 0, but we can't get this one. Good. I like this. Okay, for my last language today, I'm going to pick one that's a little bit tricky. It's a little bit trickier than the ones we've done before, for sure. And that's going to be W contains an equal number of zeros and ones. Okay, equal number of zeros and ones. Now notice, when we had them in an order like this, that was not so hard. We could switch the order around, right? But once they're out of order, things are going to get a little bit trickier. So I'm going to show you how I'm going to do this. It's kind of an interesting pattern. The idea is still the same, okay? Whenever I make a 0, I want to be able to add a 1. This says put a 0 on the left, put a 1 on the right. There's an instinct that we say, well, that's a little bit out of order, so maybe what if we wanted them the other way? We should be able to allow ourselves to do that as well. And our instinct might be that this is kind of right, but it's missing some of the strings. Any of the strings generated by this grammar definitely will have an equal number of zeros and ones. And of course, we're not finished yet. There's no terminating component of this. But the problem we might think is, even though it's not putting them in a specific order, it is enforcing some kind of order on them. On the left-hand side, so if the first symbol is a 0, the last one has to be a 1. Or if the first one is a 1, the last one has to be a 0 based on this pattern. It doesn't allow us to maybe take two strings that have an equal number and then put them next to each other. So the way I'm going to do that is I'm going to give myself some more degrees of freedom. It's saying I don't always have to grow the string from between the 0 and the 1 that I put in there. Maybe the 0 and the 1 that I want are right next to each other, and that's it. I want to grow stuff on the left of them or the right of them, or on the middle of them, or all of that. I want to grow them on the left, the right, and the middle. Okay. The only thing that's important now is I've noticed there's no terminating here, right? There's no way to terminate. And if I want to terminate, I have to terminate somehow. How can I do that? Well, either with another string that's of equal number of zeros and ones, i.e. the recursion that we've already got built in here, or the only default string that has an equal number of zeros and ones is the empty string. Okay. Now, because of all the degrees of freedom in this particular grammar, it's a little bit hard to come up with a derivation for a particular string. There might be multiple derivations for that string. It might be ambiguous to derive it. So this might not be the best grammar. We might want to convert it into a different form so that it's a little bit easier to work with. But this one will generate all of the potential strings that we need in this language. Okay, this last language helps us see that sometimes, even for the context-free grammars, that for context-free languages, that the grammars for those languages are not always going to be simple. And that just parallels what we saw with regular languages, that sometimes it's easier to come up with a regular expression than it is, say, an NFA or a DFA, or vice versa. Okay, and the same thing will be true here. It might be easier to come up with a context-free grammar, or with a pushdown automata, something that we're going to look at in a future video. All right, thanks for sticking with me in this exercise for context-free grammars. I hope you enjoyed this video, and we'll see you in that next video.